Hello, so good afternoon. First, I would like to thank the organizer giving me the scope to present my work here. Here I give the talk on based of our recent work, which we have been recently published on PRD. This work has been done with the collaboration with Francesca Calori and Pasquale Sarpico. How to use the? Oh, thank you. So, due to the time constraint, I use this cartoon picture as the outlook. The goal of this study is that we look for the dark matter signal, I mean kind of the indirect way, where the theory is that the dark matter will get scattered and then it will get captured with our chosen body. Then in the core there will be a large accumulation of the dark matter. Then they will start, and when there is a large amount of dark matter accumulation, they will start annihilating, then, but they don't directly annihilate to any standard model candidate. They will annihilate with long-lived particles, which will be long enough to escape those planets. And then our choice is to look for the gamma rays. So we also need some telescope to look for this signal. So here we use the Fermi lab. So this is the brief of my talk. So the first part is of this work is to look for the optical target. There could be several targets that could be good candidate for capturing the dark matter, starting for our Earth, Mars, Jupiter. Recently there are a few works on the Jupiter, white dwarfs, neutron stars, which is a very good candidate, brown dwarf sun. There are several works of all these cacandidates, but we need to look for the optimal target which would be good for our study. So based on that, we have categorized the condition is a 5 things like the radius, distance, density, temperature, age, where temperature and age would be the very crucial one, because we want to select those sources which should have very cold surface that would be associated with some cold core temperature. And the reason is that Sergio already mentioned, like that then the evaporation mass would be pretty low, so it would help us to probe the sub-GeV range dark matter. That is also the matter of interest of this study. And age is also a crucial one, because we would like to look for the sources where we can assume that the equilibrium reach. Because if equilibrium does not reach, then there's a possibility that we are not going to get the maximum signal. So age and temperature is the 2 crucial things. As we, apart from that, as we are also looking for the flux signal, so distance will also play a very crucial role. So we also look for the nearby object, so that will strengthen the flux limit. Apart from that, density and radius will also play a very crucial, important role. The larger the radius, the capture would be the larger. And if the density is quite dense enough, it can capture the large amount of candidate, dark matter, I could say. So based on all these criteria, we have chosen brown dwarf. So apart from all these criteria that I have mentioned, brown dwarfs have also some other advantages. What are that? The first one is the statistics. The first candidate of brown dwarfs was discovered in not very far away in 1992. But from the simulation, it is kind of predicted that there could be like 300 billion brown dwarfs in our own galaxy. So the number is pretty huge. And also there is not a very large number of detected brown dwarfs, but in future and even in the present time, there are some exploding research programs that would be focused on the detecting of the brown dwarfs. Brown dwarfs is pretty cold, so to detect the brown dwarf, we need the optical or infrared sky survey, like James Webb Telescope. So yes, and the third advantage is that as a brown dwarf don't undergo any nuclear fusion. So that keeps their temperature pretty low. So that will also lower the evaporation mass. And yeah, as I said, our motivation is to look for the sub-GeV dark matter range. So for that case, brown dwarf would be one of the exciting, powerful detectors to search for the dark matter. So based on our criteria that I have just mentioned, we have chosen 9 nearby brown dwarfs. The distance is around 11 parsec. And we take the mass for larger than 20 times the mass of the Jupiter. And from the temperature and age perspective, we choose the T-type brown dwarf. Y is the coldest one, but the mass of the Y-type brown dwarf is lower than 20 times the mass of the Jupiter. So we want to focus on the T-type one. And in respect to the age, we have chosen those sources whose ages are greater than the 2 gigayear. I think these things already discussed here, like when we start to look for the dark matter capture, or start to look for whether there is any dark matter capture in any celestial body, there should be 2 possible strategies. First is to look for the dark matter heating. If dark matter getting captured inside some body, the body will getting heated, and even if it start annihilation, that can also generate some heat. And with some optical or infrared sky survey like James Webb, we can probe or we can look for those heating. And the second was to assumption that dark matter will annihilate to mediator. That mediator will decay the bodies, and then they will decay the standard model candidate. And here we followed the second one. Yeah, I have already used this image as say outlook, where we consider the long-lived mediator. And in order to look for the gamma ray, we use the data from the Fermi-Lat. To perform the Fermi-Lat analysis, we basically follow the point-like source analysis provided by the Fermi-Lat collaboration team. We use the 13 years of Fermi-Lat data, energy between 100 to 500 GeV, and here we perform the point-like analysis, and where we consider the beam likelihood, but we did not detect any excess from their location. So next we derive the flux upper limit, and apart from that, we also perform a stacked analysis. So these are the flux limit that we obtain from all our chosen 9 brown dwarfs. This is the bin by bin differential flux limit. Here we also want to mention that we perform a model independent approach. We did not consider any dark matter model to obtain the flux limit. So all the flux that we have obtained is coming from the model independent approach. So here I want to just mention that later we will use this differential flux limit to obtain our bounds on the scattering cross section. So these are the formulation part. I won't go much detail in that because Auditro and Sharjee already give the idea of that. Yeah. Here do we give the formulation like how dark matter will get captured inside the body and what formulation we need to follow there. The second part is the crucial, like where we consider that it will get annihilated through the mediator. So this is the number of dark matter that could annihilate it over time. Here I also want to mention that I have not considered the term of the evaporation mass because for our analysis we don't go beyond 0.7 GeV. So we did not use the evaporation term. And this is the formulation for annihilation rate. So yeah, this is the total annihilation rate. And if you consider the equilibrium, like if you consider that our body already reached in equilibrium, there is an equilibrium between the dark matter capture rate and the dark matter annihilation, then we should directly use that formulation. And finally, this is the possible gamma ray flux limit, which is depend on the annihilation rate, the distance of the brown dwarf, and this is also depends on the gamma ray injection spectrum. For our cases, we have used the box-like spectrum. And in this term, the left-hand side, we have used the flux that we have obtained from the Fermi-Lat analysis. So right now I will go to the result section. We have concluded our result for 2 cases. First one is when we assume that the system reach in the equilibrium. We already if you just assume that if system reach in equilibrium, So what bounds we can obtain from that? So this is the bound. Here we use the formula flux upper limit and translate that limit to the scattering cross section. These are the limit obtained from all 9 brown dwarfs, and the black one is the stacked one. Here I also want to mention that in case of, as I already told about the mediator, long-lived mediator, from our analysis we also give a very wide bound on the mediator. The bound is that, as we are considering that the mediator should leave the celestial body, so it should be larger than the radius. And second one is that as we are performing the point-like analysis, so it should also agree with the angular resolution of the Fermi line. So based on that, these are the bound we provided from our analysis. And the second thing is that here we did not consider the system is in equilibrium. We just take the real age and try to see what bound we can expect from that. So in case we need to follow this formulation where you use the annihilation rate obtained from the Fermi Planck for S wave. And here you can see V annihilation the containment volume where the accumulation and annihilation will take place. It is a function of the core temperature and core density of the brown dwarf. So in this table I have given what is the possible core temperature and core density for our chosen sources, and these are the bound. So here you also, next slide. Here, next slide I will like to discuss like whether by assuming equilibrium, are we overestimating our limit or they are just comparable enough. So this is the impact of the equilibrium hypothesis. Like this is the formulation for the equilibrium time scale, which depends on the annihilation cross sections, also the core density, core temperature, core density. Here you can see the equilibrium time for certain conditions for our all sources. So here you can see, if you could remember, that we chosen those brown dwarfs whose age are larger than 2 gigayear. And here you can see the equilibrium time scale is not greater than 0.5 gigayear. So from here we can just say that the brown dwarf that we have chosen, equilibrium hypothesis actually justifies well. And here we have given a plot between the limit that we have obtained from the equilibrium hypothesis and obtained from the red one is from the considering the real age, and you can see they are pretty comparable. They are just differ by 1.26 factor. So, but here I can comment that the real age could be the most realistic one. But yeah, in case of even we are considering the equilibrium one, we are not going to overestimating anything. So final part, we also perform a comparative study with other literature study. Here our main interest was to make a comparison with the limits provided by some direct detection, like some PICO, xenon, CDX, which are performed for very sub-GeV range. We can see in compared to the xenon and PICO, in compared to the CDX and xenon, our limits gives a better constraint, not in case of the PICO 60, but for other two we can get the better limits. And also, there is also some other comparison with the Jupiter one by Lebesgue. We can see the Jupiter limit is kind of 5 orders or few orders more stringent, but here you want to mention the Jupiter is more like 5 lie around 5 astronomical units, pretty closer compared to our chosen brown dwarfs. Here I mentioned about that. So in that case, and they are using the same approach, like they are considering the point-like analysis for formula data. So in that case, our chosen bound over the mediator lifetime could be pretty broad compared to them. And we also perform a comparison with some similar study where one of the recent study by Lebesgue, where they performed this study for the galactic center population of brown dwarf. We can see our result kind of comparable to them, but here you want to mention that our analysis, we just consider the sources from solar neighborhood, and it does not much dependent on the density profile. That we have chosen the NFW, but we have checked with the Booker profile, but it does not change much. But in case of the galactic center population, we check that it also depends on the density profile. If we use the Booker one, it will just, the limit will be worsened by 1 factor. Our code is already also available over GitLab and Escape OS. So these are the final outlook. So as I already said, we performed a model independent study where we used the formula data. We did not find any emission, but our limit shows that especially at the sub-GeV range can provide a very comparable or sometimes even better constraint compared to some direct detection limit. And in future, we also, when with the JWST or some other sky survey, when we have large amount of data, large amount of detected brown dwarfs, the statistics will be very improved. So then we can also get very, better limits that we are reporting here. So thank you.
Any questions? Actually, I want to ask a question. So about this long-lived particle that you mentioned, right? If they're too long-lived, then you might they might move quite far away from the brown dwarf to be seen as.
Yeah. Here I have mentioned the limit about the.
Okay, so this is the range.
Yeah, this okay. The larger limit is obtained from the formula resolution. So it should be detected by the formula. From there we get the larger limit, and lower is the okay. It should.
And usually when you have a decay actually outside of the star, the spectrum, because of kinematics, just creates sort of like a box distribution of.
Yes, yeah. So, for the point-like sources, we have used the box.
Okay, all right, okay, all right. Thanks. Any question? All right, so let's thank our speaker again.